Are you struggling to understand process engineering diagrams? Or maybe you're not quite familiar with them at all? Make no worries, I got your back. Hey, what is up guys? Welcome once again to the channel. It's always great to have you back. And guys, I'm pretty sure that you are quite familiar with a lot of process engineering diagrams. You may be quite familiar with the block flow diagram, you may be kind of familiar with the piping and instrumentation diagrams, and you know that there's a lot of other type of diagrams depending on the discipline that you may be working in. And I'm talking about electrical diagrams, maybe mechanical pieces, maybe we're talking about civil engineering or control processes. Whatever the area that you may be working, engineering diagrams are there for sure. In this specific video guys, what I'm going to be doing is showing you the most common type of engineering diagrams that you are going to encounter in the chemical process industries. And all these guys using a single example, the ammonia plant. And before we even continue guys, I just want to refresh the ammonia process because I'm pretty sure that many of you may know it by heart. It's by far one of the most common examples used in the chemical industry. But if you're not quite familiar, make no worries, we're going to be checking this out. Let's focus our attention into the ammonia production plant. Well, typically you will be using the Haber process or Haber-Bosch process, which is essentially the conversion or transformation of hydrogen gas and nitrogen gas into ammonia. Of course, we're going to have a lot of processes in between, and we're going to cover those. But right now, what you need to understand is that this is at relatively high temperatures and very high pressures under the presence of a catalyst. Essentially, we have two gases, nitrogen, hydrogen, and we're converting into ammonia. And this will be a typical ammonia plant that you will encounter out there. And this is the specific description of the process, which, of course, I'm going to ask you to pause and read. The main idea of this video is that, of course, a picture is worth 8,000 words, guys. And what I mean with this is that, yes, we want to have engineering diagrams instead of having to read a lot. And when I mean a lot is not only that. Of course, you can read this for this specific engineering application. If you're talking about electrical appliances, if you're talking about mechanical equipment, if you're talking about chemical processes, you're going to encounter a lot of things that if we were to write sentences, we're going to take a lot of time. Hence, the importance of understanding process engineering diagrams. The very first thing that pops into mind will be a photograph, maybe an aerial photograph, and marking one by one the processes, the general processes. Of course, we're not going to have the identification of every single process or unit operation, but the general processes. And I'm going to assume that you read the process because we're going to see what is this. Number one will be the sulfurization units, which are going to be removing the sulfur of our steam reforming units. Then we have the primary reformer, which is number 2. Then goes number 3, high temperature and low temperature shift reactors. The name implies we're going to be creating the syngas. Then we're going to be removing the carbon dioxide, and then we have the stripper, which is going to be recovering our solvent. Then we have the ammonia converter. You could say that this is the actual ammonia reactor. And then we have the liquefaction right here and storage. Finally, we have the pipeline if you're talking about distribution, but generally speaking, this will be a process. Of course, this is already a great overview of the process, guys. But as an engineer, we need to further simplify this. And the very first idea of the simplification of a process, I would say, that is the block flow diagram. As the name implies, you can see that these are blocks. So literally blocks right here, right here. Sometimes you can encounter different shapes, maybe a circle, ovaloids, maybe a triangle or so. But generally speaking, we want to stick to simple figures. Let it be a rectangle, square, arrows, and so on. It's a simplified representation of the major processes. We were talking about the sulfurization, the reformer, the reactor. We were talking about the ammonia production. We were talking about the CO2 removal, water shift reaction, and so on. So all the main units are here. And this will help you understand the process. There are no specific rules, guys, so there's no specific requirement for you to show one unit or several units. The size of arrows don't care that much. Typically, we want to show big arrows as main or major pipelines, but there are no specific rules. And the main use of BFDs are high-level process overviews. You want to understand the conceptual idea of the process. Of course, once you understand this, you can get into deeper knowledge. In this specific example, guys, we have feedstock, which is natural gas. Then we will have air, which contains nitrogen. And then we will have the hydrogen gas, which comes typically from the natural gas. We're not showing that much into the process, but generally speaking, you have the feedstock, you have secondary streams. For instance, steam, we have flue gas, we have air, we have CO2. Then we have the main process units. For instance, these blocks will be considered main processes. If you are adding the cooling or heating of the processes, those may be considered as secondary units. No conditions are set. You can add them if you want. For instance, if you want to add temperature or pressure, but typically in a BFD, you're not going to encounter this. No instrumentation if you don't want to add. Of course, if you think it's relevant, you may be adding a valve right here, or maybe you want to add that this is a pneumatic line. Maybe you just want to add that there's a check valve and so. And well, there's no piping specifications. You don't know the size of the pipeline. Once again, if you want to add that information, you can do it without any problem. But the idea is that a block flow diagram does not require all these specific information. No unit specification, no unit sizing. Now, the second diagram that we're going to explore is the process flow diagram. And this is by far one of my favorites because you can show a lot of data, a lot of detail, and there are not so many rules. So it's quite flexible. And this is the one that you're going to encounter the most students and young engineers working with because, as stated before, there are not so many rules. You can add the control loops if you want. You can add simplified versions of the process. You can condense units and so on. So what are the main rules? You can see here, we have no single blocks. We have more like a specific figures that resemble processes or equipment. For instance, here we can assume that this is a column. We can assume that this is a compressor because of its shape. We can see that this is heat or cooling equipment. We can see that this is a furnace. We can also see that there's several temperatures, pressure conditions along the processes. We have some tags. We have these green arrows, which are essentially the inlet material maybe. We have, the final product, which is the ammonia, secondary processes or products, byproducts. And as you can see, guys, this is a detailed graphical representation of the process, or as I like to say, a more detailed version, because technically speaking, you can go back into the block flow diagram and say that this is a process flow diagram, because as stated before, there are no specific rules for this. So the important part is, of course, to understand the flow of materials. So yeah, arrows gotta be there present, and something that resembles equipment. For instance, this part right here, the reformer or reactor. And the typical applications, guys, will be for process design, development, optimization, a very quick review of the process. Yeah, it may be quite detailed if you want to, but generally speaking, there are no specific rules. And actually, this is the ammonia process, guys, remember? And in this specific example, we have a more precise drawing if you were to compare it to the block flow diagram. In the block flow diagrams, we didn't know the compression part, we didn't know about the flashing, we didn't know about the CO2 absorption or the units that were involved, and now we have a better understanding. We have more primary and secondary streams. Secondary streams are quite common in process flow diagrams. We may add process condition, even though it's not a rule, but it's quite common to add process conditions. We have more individual units, as you can see. We have coolers, we have chillers, we have heaters, compressors, pumps, etc. As stated before, you're going to encounter more sub-processes. It's quite common that the more in detail you go, you're going to encounter more unit operations. Not because in the block flow diagram they didn't exist. Simply, we're just simplifying the process. Once again, no piping info, no instrumentation, and no layout or proper sizing. This is the third type of diagram I want to show you, and I'm pretty sure that many of you know that this is by far one of the most common type of process diagrams used in the industry. And I'm talking about the P&ID, the piping and instrumentation diagram. And as the name implies, we're going to be focusing our attention, yes, into the process, but also into piping and instrumentation. Because piping is, of course, very important once that you're taking into consideration all these things. And especially when you're talking about different processes, you want to know what are the actual sizes of the pipelines, what do they contain, what do they have. And moreover, guys, I would say that the control aspect of the process is very important if you're actually working in the industry, because many times I see that the engineers make process flow diagrams just taking into consideration several aspects, but not all of them. And one of those is, of course, being able to control the process. So what we have here, we have detailed piping. Actually, we're going to see later on, but if you were to zoom in, actually, you can download this image. If we were to zoom in, you will encounter the specifications of the pipelines, guys. Not only that, equipment is present. We have a blower right here. We may encounter a ammonia line right here, a valve. Valves are quite common in these type of diagrams. Instrumentations, you can encounter sensors, maybe level sensor, a temperature sensor, actuators, control devices, and so on. All these little squares, we're going to explore them later on, but these are very common to see in a piping and instrumentation diagram. When do we use these type of diagrams? Well, in detailed engineering phases in which we need to show the client what we are doing. In construction phase, we need to know which place is going to be designed for a sensor, or if we need to adapt a tank, if we're going to be adding a specific function or a specific instrumentation. And of course, when you are already operating, because you want to understand the process and you want to know where to find the temperature devices, the pressure devices, where are these measurements being taken, how are they being taken, if they are working properly, and so on. More information on the piping and instrumentation diagram. There's no specific feed or stream information. As you can see, these are tags showing the inlet, but you don't know the composition, you don't know what's inside, you just know that there is a stream. There's a detailed instrumentation stated before, guys. You can see control loops, controllers, interlocks, and alarms. Very likely you're going to see all the utility streams that are being used in the process. Detailed unit operations, as you can see, not only a block, you're going to see that the block has valves, they have sensors, they have control loops, and so on. And one important aspect, guys, is that sizing here doesn't matter that much. So yes, of course, you want to try to keep a scale, make kind of sense that, of course, a column is going to be way big compared to a valve. But in real life, you're going to see that a distillation column is huge compared to a valve. And in a diagram, you can encounter that these are very similar in size, or at least they don't make that much sense with respect to a scale. So very importantly, P&ID will not have a scale. Moreover, you're going to encounter a lot of valves and piping. This is by definition the diagram that includes that. Also, you may think that electrical wiring or electrical specifications are quite common to encounter in here, and truth be told is that no, you are not going to encounter a lot of these, and as a process engineer, I'm pretty sure that you need this. And what you need to do is, of course, go back, check out electrical wiring diagrams. Let's continue, and I'm going to get a little bit faster with the following diagrams or drawings. Layout diagram, as you can imagine, is, well, the layout, where are they going to be located physically, of all the piping equipment and fittings. I'm talking about valves, instruments, and so on. It's very common because you want to know where are they going to be physically. You want to be able to find them when you are looking. It's like a map. And well, if you're installing, maybe you're working in maintenance or simply operation, you need to know where the equipment is located. Typical examples of what you may see in a layout diagram will be the area locations, support facilities, storage, handling areas, access of circulation, maybe a hallway, which places are allowed to walk, which places are not allowed for personnel, and so on. And typically you will not see the tile equipment specifications. Maybe if you're talking about a tank or a reactor, you're just going to encounter the size of the vessel, not that much on the capacity, flow rate, and the conversions and all that. You're just going to find where is the pipe, but you're not going to encounter what does the pipe contains or what is being measured there, if there's temperature, pressure, density, concentrations, or so. As stated before, electrical wiring is not likely to be present in this type of layout diagrams. This is another example, guys. Try to figure out. This is also available for download, but check out all the content and try to recognize what is this. Remember that the main idea is that we are still talking about the ammonia process. Isometric drawings. And technically speaking, isometric drawings, as the name implies, are drawings that try to force scales to be the same. But the reality is that isometric drawing is most likely to be encountered in pipelines. Try to imagine that you want to model some momentum transport in pipelines. Well, you will love to know the length of the pipelines, if there's any angle, if there is any increase in the pipeline, if there is a fall in the pipeline, or maybe we are bringing up our fluid, and this diagram is perfect for that. It's going to tell you the angles, it's going to tell you the length, and it's going to tell you most likely the type of pipeline and the characteristics. I really love this one because you can make it as simple as this one right here, or you can make more 3D diagrams like this, more friendly for the user, or simply stick to the traditional diagram right here. We continue with elevation diagrams, and yes, as the name implies, we're going to see how elevated are equipments. Now, in real life, guys, when you go out there, and I'm saying this for those that may not be quite familiar with chemical industry, is that you're going to encounter a lot of equipments that may not be at ground level. They can be actually in the second to third level. They may be contained in a set of 7, 8 levels. For instance, a distillation column. A reactor may be at half level. So yeah, it kind of doesn't make that much of a sense unless you think of a chemical plant as racks. When you have racks, metallic racks, you can install such equipment. And this is very common to encounter with elevation drawings. For instance, now of course you can encounter other type of drawings. For this, I present you the 3D or CAD drawings. These are three-dimensional representations of equipment, process plants, pipelines, valves, whatever thing you can imagine. The AutoCAD or any CAD is going to be able to work with that. Now, it's used mostly for visual or visualization, virtual walkthroughs, so you have a better understanding of the render of the equipment. There are no specific rules. The most obvious one will be, of course, it's gotta be the real sizes, because we're talking about visualization. It's gotta be the actual physical aspect, but there are no specific rules with respect to size, colors, scales, and so on. And yeah, finally, what you will not typically see in a drawing will be a detailed equipment specification. This is more visual. It's not more about understanding the process, rather the actual sizes or the render of the chemical process or the equipment. No process flow details. So let's see, if you wanted to know what's inside this pipeline, what's the temperature, what's the process, you are not going to encounter that. And finally, guys, you're not going to see operational procedures, how to open a valve, how to close, how this distillation unit is working, the flow rate, the recycle, all these little details that are properly of the process. Well, as said before, this is just a visual element. Let's continue with the HAZOP diagram, guys, and as the name implies, it identifies potential hazards and operability issues in the process. Actually, I don't want to get that technical or detailed, but it's essentially a diagram that is used to find very specific things that may be converted into an accident or incident or something like that. Cause and effect diagrams, these are very common, guys, actually not unique for the process industry, but it really helps to try to solve problems, specifically when you don't have any idea of where the problem is coming from. So the best idea or the most logical setup will be try to bring all the things that we know that are involved and suddenly just checkmark everything that is going on. For instance, if we are having quality defects, well, we know that measuring could be going wrong. If we're talking about electrical power, we may be talking about electrical interruption or fluctuation of the voltage, and so maybe we have a machine that is not working properly, we install something correctly or so. Suddenly you want to identify which of all these elements are the things that are producing the defect on quality. Loop diagrams, guys, we're going to see those later on, but as you can imagine, these are essentially diagrams that show you the logic behind the control loop. And I don't want to get that technical right now, but essentially we're going to be covering how the sensor is working, the transmitter, the controllers, the actuators, and eventually the logic behind that control system. We can encounter also process network diagrams, guys, and we have much more diagrams. For instance, the pinch diagram for heat and energy balances, guys. We got the Gantt chart, which is for project management, working tasks with people, with teams, trying to find the bottleneck in the work or the organization. Sankey diagrams, guys, and many other type of diagrams, guys. I'm pretty sure that you are fed up with all these diagrams and drawings, and we're going to explore even more. But for now, I really think that we cover a great amount of diagrams, guys. And all these, guys, to explain the ammonia plant. We want to explain this process right here, the aerial photograph and the horizontal photograph of the chemical plant. So probably you are wondering, guys, what is the best diagram for process engineers? Well, the answer will be there's no unique solution. It really depends on the best fit for your needs. If you're working a lot with control process, well, maybe process flow diagrams and of course the process and instrumentation diagrams and control loop diagrams are going to help you the most. If you maybe want to learn more about the location of the facility, the dimensions, the sizing, well, elevation diagrams may be the best fit for you. Also, a AutoCAD drawing will be great for you. Or if you're working with pipelines, you're working in the utilities, maybe you work with steam, you're working with water, you're working with air and all these things, maybe isometric drawings will be the best fit for you. So as stated before, guys, there's no unique solution for what's the best diagram. It really depends on your needs. And after all, you will be the one working with such diagrams and drawings. I really hope that this video helped you to have a better understanding of what are the relevant diagrams for a process engineer and more importantly, the power of such diagrams. I really tried my best to condense the information, guys, and there you have it. And before we go, what is your favorite diagram? Do you have a specific pick or maybe I missed one that you think is quite relevant for process engineers? Please let me know in the comment section so we can discuss it further. On my behalf, guys, that will be it. I'll see you in the next lecture. And by the way, guys, if you're enjoying this video, please do not hesitate to check out the course, the ultimate guide for process engineering diagrams and drawings. I'm pretty sure that you're going to like this course.